I'm going to tell you a story about a math problem. The date is February 28th, 2020, and I am in the middle of training for one of the hardest challenges of my life. That's me in the back with the white shirt. In just a few months, I'm planning to run a 100-kilometer ultramarathon through the Santa Cruz Mountains, just south of San Jose, California. If that sounds impossible, you're probably right. Though I would consider myself an experienced runner and marathoner, I had serious doubts as to whether I would be able to finish the race, even if all my training went as well as I could possibly hope. Of course, I never got to find out. Just a few weeks later, COVID-19 swept across the globe, and my running friends and I, who would normally spend our weekends rampaging through the wilderness, instead found ourselves under lockdown, prohibited from traveling more than just a few miles from home for exercise and other essential activities. But what happens when you tell a bunch of ultra runners that they're only allowed to run the roads and trails in their immediate neighborhood? The answer is that they run every single one of them. And so, out of the global pandemic, the Run Every Road Challenge was born. The idea is simple. Step out your front door, traverse every single block of every single road in your neighborhood, and return home. At the time, I was living and working as a software engineer in Silicon Valley, and as you might expect, even the runners in the area tend to be a pretty nerdy bunch. It wasn't long before someone asked the question that we're going to tackle today: given a particular neighborhood, what algorithm can we use to find the shortest possible run that completes the challenge? Good morning, Internet. I am Matt Buyak. Welcome to my channel. I usually cover topics in programming and computer science with a focus on problems from the websites projecteuler.net and onlinejudge.org. But today, we're doing something a little bit different. As part of the Summer of Math Exposition 2023, we're going to find out how to run every road. So, typically, with the kinds of problems I solve on this channel, we can just jump directly into the math. But for this problem, before we start talking algorithms, we need to find a way to turn this, my old neighborhood in San Francisco, from a collection of trees and buildings, cars and stoplights, into some kind of symbolic representation we might feed into a computer or manipulate with pencil and paper. Since our goal is to run every road in the neighborhood, the first step is to decide what we mean by a neighborhood. Back in 2020, when I was first trying to tackle this problem, I just went to Google Maps and did a search for Noe Valley. Weirdly, the reported boundaries of the neighborhood have changed significantly since then, but at the time, Noe Valley was considered to be the area between 21st and 30th Streets, bounded by Dolores in the east and Market and Diamond Heights in the west. Next, we need to decide what we mean by a road. It may seem like the answer is obvious, but in order to translate our problem into the language of mathematics, we need to be very precise about what we mean. Major thoroughfares like Castro Street should definitely be included, but what about this? Well, unless you're looking for a different, more fateful kind of cable car experience, or perhaps a little chat with the San Francisco Police Department, I would suggest not. But what about narrow alleyways like Comerford Street? Or to give a more extreme example, Severance Street, which is barely more than a driveway. And what about actual driveways that look more like streets, such as these, just off of Castro and Carnelian? And what about stairways? And whatever this is, do those count as roads? I suppose not, though it's a bit of a shame since Noe Valley has so many wonderful stairways. But even if we decide not to count them as roads, they do raise another important question. Often these stairways act as shortcuts between otherwise disconnected areas of the neighborhood. Are we allowed to use these shortcuts as long as we still fulfill the requirements of the challenge? That is, we need to run every road, but are we restricted to running only the roads? Fortunately, it won't change our analysis of the problem very much, so we'll set that aside for now and address the question later when it becomes relevant. In the end, I decided that anything on Google Maps with a name ending in street, boulevard, court, place, terrace, way, drive, or lane would count. My definition was immediately challenged, however, when I discovered that Sapphira Lane looks like this. Nice try, Sapphira Lane, but you're going in the stairs category. So now we've decided what counts as a road, but is there ever a case where one road might count as two? For example, Dolores Street has a wide median down the center, and other streets such as Cesar Chavez and Grandview are split in places. I decided to count only Cesar Chavez as two streets since each half of the split is two-way rather than one-way. Keep in mind, these questions don't have one right answer. It is somewhat arbitrary what counts as a road and what doesn't. What's important is that we have clear answers to these questions before we start on the math. Going back to our neighborhood, now we can mark everything we've decided to count as a road. Next, we need to decide what counts as an intersection. While the decision of what counts as a road was somewhat arbitrary, we have to be a bit careful with how we define our intersections. We'll want to be able to describe any particular road segment as connecting two intersections. So we actually need to consider the end of a dead-end road to be an intersection, even though there's just one road there. On the other hand, some locations which are definitely intersections in real life, like the corner of 30th and Dolores, don't actually need to be included because they're at the edge of the neighborhood and we have no choice but to turn there. There is at least one judgment call we need to make. In particular, how many intersections do you see in this map? If you said 3 or 4, maybe seeing the area from ground level will change your mind. In any case, I decided to count it as 2 intersections, one at 21st and Grandview and one at 21st and Worth. Just be glad there aren't any traffic circles in Noe Valley. Going back to our map again, we can mark every intersection in the neighborhood and give each a unique label. Last, we can actually get rid of the map, at least for the moment. Now this is starting to look like something a computer might understand. In computer science and discrete mathematics, we call this a graph, which is one of those horribly overloaded terms that has at least 5 different meanings. But for this video, a graph is a collection of points, called vertices or nodes, connected by lines, called edges. Also, our graph is technically a weighted graph because each edge has a numeric value associated with it. For example, the road segment which includes Market Street has a length of 1,280 meters, so its weight is 1,280. There isn't enough space on one slide to show the weights for every edge, but just keep in mind that that information is part of our graph. Also, unlike points in geometry or trigonometry, which typically have an x and a y coordinate, the vertices in our graph are coordinate free. That is, we aren't concerned with how the vertices are laid out in space. What matters are the connections between the vertices. And that means we're free to rearrange the vertices however we like, if it will make the graph easier to read and understand. Now we're ready to restate our problem in the language of graph theory. We want to find a sequence of vertices such that each pair of vertices in the sequence is connected by an edge, and the first vertex in the sequence is the same as the last. This is called a circuit. So we want to find a circuit which includes every edge and has the minimum possible weight. In computer science, as in mathematics more generally, when presented with a new problem, a good strategy is to look for similar problems with a known solution that might be adapted, or at the very least, might have some useful techniques we can reuse. 2 famous problems that will seem very similar to ours are the bridges of Königsberg and the traveling salesman problem. And both of these turn out to be important to our story. Curiously, one of these has a trivial solution and the other is almost impossible. As I describe the 2 problems, try to note the ways in which they differ slightly from our problem, and also maybe see if you can make a guess as to which one is easy and which one is not. First, the traveling salesman problem. This is possibly one of the most famous problems in computer science, and even if you've never heard of it, there's a good chance you could guess the premise from the name alone. The idea is that in the days before Amazon and the internet, our proverbial salesman would have a list of cities they would need to travel to sell their wares. And in order to minimize time on road, money spent on gas, etc., the salesman would like to find the shortest tour that visits each city exactly once. For example, this map shows the shortest path which would visit each of the state capitals in the contiguous United States. The problem is to find an algorithm that always finds the shortest tour for any list of cities. The second problem is the bridges of Königsberg. As the story goes, the citizens of 18th century Königsberg would stroll through the city, crossing its 7 bridges, and they would wonder whether it was possible to find a route through the city that crosses each bridge exactly once. We would like to find some criteria that can be used to answer this question not only for the city of Königsberg, but for any arrangement of rivers and bridges that we might imagine. So all 3 of these are touring problems, but each is slightly different from the others. For the run every road problem and the bridges problem, we're visiting each edge of the graph at least once, while the traveling salesman would like to visit each vertex of the graph at least once. Also, the run every road and traveling salesman are optimization problems. That is, we're trying to find the best solution out of many that are possible, while the bridges problem is a feasibility problem. We're only concerned with whether a solution is possible at all. Now, I think it's not immediately apparent which of these is trivial and which is not, but it turns out that the bridges of Königsberg was solved by Leonhard Euler in 1736, while for the last 20 years, the Clay Mathematics Institute has offered a $1 million prize to the first person who can find an efficient algorithm for the traveling salesman problem. And thus far, there have been no takers. So is our problem more like the traveling salesman problem, or more like the bridges of Königsberg? Well, since the bridges problem has actually been solved, it seems that might be a more promising place to start. We'll begin by taking a look at Euler's approach with an eye toward how we might adapt his techniques to our run every road problem. The original problem Euler solved was focused on the 7 bridges of Königsberg. 1, 2, 3, 4, right. Apparently the British blew up 2 of the bridges during World War II when the city was occupied by the Germans. So we'll just add those back in. There we go. 5, 6, we still seem to be short 1 bridge. Oh, I see, it's farther down the river. And now we have 10 bridges. Right, so these weren't here 300 years ago. But if we take the historical 7 bridges and do something similar to what we did with our neighborhood, with bridges acting as roads and landmasses acting as intersections, we get a graph that looks like this. Now, I would love to show you the tour Euler found crossing each of the bridges exactly once, but I can't because Euler's solution to this problem was actually to prove that it's impossible. That may seem like a disappointing result, but the techniques that Euler used in his proof were so insightful, they essentially gave birth to the subject of graph theory. Euler's key observation was that any circuit through a graph must arrive and depart from a particular vertex the same number of times. So if each edge is crossed exactly once, there must be an even number of edges connected to each vertex. In graph theory lingo, we say that each vertex is of even degree. Maybe the easiest way to see how this works is to start with an arbitrary tour and build up the corresponding graph one edge at a time. Note that we don't have to have the full graph in advance in order to confirm that this is a valid tour. We just need to check that the first and last vertex are the same and that no edge appears in the tour more than once. Now that we know our circuit is valid, let's begin our tour. After we traverse the first edge, we have two vertices of odd degree, and all other vertices have even degree because they have 0 edges. Remember, the degree is the number of edges connected to a particular vertex. Also, note that I've color-coded the vertices based on whether they have even degree or odd degree, with even vertices being blue and odd vertices being orange. This is a convention that I'll use throughout the video. When we add a second edge, the vertex from which we just departed switches back to being even, and the vertex where we just arrived is now odd. As we continue through the circuit, the only vertices with odd degree will be our starting point and our current location. All other vertices will have even degree. Now, in order to return to our starting vertex, we'll need to add an edge which connects the only two odd vertices in the graph. That means all vertices are left with even degree. As we continue our tour, we will always have exactly 2 odd vertices, or if we return to the start, we'll have 0 odd vertices. That means when we finally complete our tour, each vertex must have even degree. This kind of graph, which has only vertices of even degree, is known as an Eulerian graph, after Leonhard Euler. And a circuit which visits every edge exactly once is known as an Eulerian circuit, or Eulerian tour. We've just shown that it's only possible to find an Eulerian tour in an Eulerian graph. To be fair, the names would be very confusing if that wasn't the case. Taking another look at our bridges and color-coding the vertices based on their degree, we see that not only is this graph not Eulerian, in some sense it's as un-Eulerian as it could possibly be. Every vertex is odd. That means we know from the proof we just did that historical Königsberg had no Eulerian tour. In the last section, we showed that we can only expect to find an Eulerian tour in a graph where every vertex is connected to an even number of edges, a so-called Eulerian graph. But is the reverse also true? That is, if we start with an Eulerian graph like this one, can we always find an Eulerian tour? And if so, how do we do it? Let's try building an Eulerian tour one edge at a time by wandering through the graph. But to make sure we don't traverse the same edge more than once, we'll remove each edge as we cross it. This is kind of like the reverse of the demonstration we just saw. Instead of building up the graph one edge at a time, we're going to tear it down one edge at a time. We'll begin at an arbitrary vertex and take a step in an arbitrary direction. As we do, we remove that edge and set it off to the side. You'll see, like before, only our current vertex and our starting vertex have odd degree. Every other vertex has even degree. Since we really don't know where we're going, we'll just wander through the graph, removing edges as we go. You'll see that at each step, it's still the case that only our starting and current vertices have odd degree. Now, you might be concerned that at some point we could run into a dead end. That is, we might arrive at a vertex which has no edges remaining. But that's impossible because our current vertex always has odd degree. That is, there's always at least one edge we can use to continue our wandering. There is one exception, however, which is our starting vertex. If we should happen to return there, we may indeed find ourselves at a dead end. It's significant, though, that we have found a circuit through our graph, just not an Eulerian circuit. That certainly seems like progress, so let's set that circuit aside, pick a new starting point in the graph, and continue the process. We may have to restart the process multiple times. Eventually, we will have decomposed our graph into a collection of loops. But we can actually combine all our separate loops into one big loop. First, we find a vertex that appears on two different loops. For example, we could use vertex A, which appears on all three loops. We know such a vertex has to exist because if it didn't, each of our loops would have to be its own island, completely separate from each of the other loops. Now we'll rotate the loops we wish to combine so that they both start and end at the chosen vertex. That is, regardless of where we originally started, we're free to begin at any point in the loop and follow it around until we return to our start. This loop originally started at vertex F and traverses clockwise. But it will be just as valid to begin the loop with vertex A instead. These loops are essentially equivalent, and we can replace one with the other. Next, we can repeat this process with the center loop. Previously, we started with vertex C, but it will be just as valid to begin with vertex A. And again, we can swap the rotated version of the graph for the original. Now, since the left and center loops both start and end in the same place, we can trivially combine the two. We just traverse one loop, immediately followed by the other. Repeating this process multiple times, we can eventually combine all our loops into one big loop which visits each edge exactly once each. Note that this tour is different from the one we originally started with. For any given Eulerian graph, there may be many possible Eulerian tours, but we've just proven that there must always exist at least one. In the last section, we showed how we can use this algorithm to find an Eulerian tour. That is, a tour that visits every edge exactly once. So what are the implications of this algorithm on our original problem, the run every road problem? Well, if your neighborhood happens to only have two-way and four-way intersections, we can use this algorithm to solve the run every road problem for your neighborhood. But unless you've been very creative in how you drew your neighborhood boundaries, that seems pretty unlikely. Even if your neighborhood is a very regular grid pattern, there's a good chance you created some three-way intersections when you drew the border of your neighborhood. So is there some way we can make our neighborhoods with three-way and five-way intersections look a little bit more Eulerian? We'll use this graph to help us investigate how we might accomplish that. It doesn't correspond to any real-world neighborhood, but has a number of characteristics that make it a good test case. It has vertex degrees ranging from 3 all the way up to 8, and is also more interesting than a completely regular grid, without being too chaotic. Taking inspiration from our look at the bridges problem, we'll start by coloring each vertex based on whether it has even degree or odd degree. Next, let's consider an arbitrary solution to our problem. At this point, we're not necessarily concerned with whether this is a good solution. We're mostly just interested in what properties it might have. It starts off with a reasonable approach, traversing each row of the grid to get all the horizontal edges. Then, after we run out of horizontal edges, it begins to traverse the columns to pick up the vertical edges. But when it reaches vertex C, we have a bit of a problem. In order to continue with the next column to the left, our path must traverse the edge between vertices B and C for a second time. Since our goal is to make our graph look more like an Eulerian graph, rather than traversing that edge again, we'll just add a second edge between vertices B and C. Just like that. And we do the same moving from vertex V to vertex U. At this point, after finishing the rows and most of the columns, it starts to become less clear what a good path might look like. We wander through the graph, making our way to edges we haven't visited yet, and adding duplicate edges wherever necessary. In some cases, we may even need to add a third edge between two vertices. Eventually, we finish picking up the remaining edges and complete our tour. Now, as desired, we have transformed our original graph into an Eulerian graph. That is, every vertex has even degree. Going forward, I'll refer to this kind of graph as a solution graph or candidate solution graph. This is in contrast to our original graph or problem graph. To be a bit more precise, we'll define a solution graph as an Eulerian graph with all the same vertices as our original and at least as many edges for each pair of vertices as the original. Note that we're specifically not defining this graph as being constructed in the way that we just did. This leaves us free to possibly find solution graphs using other methods. Now, because our solution graph is Eulerian, that means we can use our algorithm from the bridges problem to find an Eulerian tour through the graph. But we also know that there may be more than one possible tour. It might be hard to believe, but even a small graph like this one can have trillions of possible tours. How do we find the one that is optimal? Fortunately, because every tour traverses each edge of the solution graph exactly once each, the total weight will be the same for every possible tour. This is actually a critical observation because it means we don't have to worry about the exact path of our solution anymore. If we can find the optimal solution graph, the bridges algorithm will give us a solution with the minimum possible weight. So how do we know when we have the optimal solution graph? Well, to start with, those triplicate edges don't seem very optimal. In fact, any pair of vertices where we have more than one edge seems like a possible area of improvement. And so we'll introduce a third type of graph, the difference graph. As the name implies, the edges of this graph represent the difference between the original graph and the solution graph. Or the other way around, if we add the difference graph to the original graph, it gives us our solution graph. That means if we can minimize the total weight of our difference graph, we'll also be minimizing the total weight of our solution graph. Notice that when we compare the difference graph to the original graph, we see that every vertex is colored the same way in both graphs. That is, whether a vertex has even degree or odd degree doesn't change between the two graphs. That's because subtracting an odd number from an even number gives another odd number, and subtracting an even number from an even number gives another even number. And in fact, this is the defining characteristic of a difference graph. If we take any graph whose vertices would be color-coded the same way as the original graph and add it to the original graph, the result will always be a valid solution graph. But we're still left with the question of how we find the difference graph of minimum weight. In the last section, we looked at how we can use a difference graph like this one to generate a candidate solution graph for our run every road problem. To get a better understanding of such difference graphs, we might see if there's some way we can break them down into smaller components, similar to how we gained a better understanding of Eulerian graphs by breaking them into circuits. Now, we won't be able to break difference graphs into circuits because of the odd vertices, but what we can do is break them into paths. There are a number of ways of showing that this is always possible, but here's my favorite. First, organize the vertices of odd degree into pairs. Note that the vertices in each pair don't have to be connected, or even be close to each other. Next, we'll add a fake edge for each pair. These edges don't even need to exist in the original graph. They're just placeholders for argument's sake. Note that the resulting graph is now Eulerian, so we can find a tour. Remember, that means breaking the graph into cycles and then combining the cycles into one big tour. Now, here's the trick. In the tour we just found, remove all the fake edges we added earlier. This breaks the tour up into segments, where the first and last vertex in each segment has odd degree. That is, we've successfully decomposed our difference graph into paths. Note that if we recombine these paths, we get back our original difference graph. Since this process will work with any difference graph, in particular, it must work with the optimal difference graph. That means if we can find the shortest paths connecting our odd vertices, that will give us the optimal difference graph. So what do you think? Is this difference graph optimal? I'm guessing you might find this path to be a bit suspicious. But remember, we can't tell just from the visual representation whether a path is optimal or not. We have to look at the actual weights for each edge. But just to make things simple for this example, let's use weights for our edges that actually do match the visual representation. From here, we can use well-known graph theory algorithms for finding the shortest path between two vertices. This is the sort of thing that might be covered in an introductory course on algorithms. But if you're interested in the details, you might want to read up on Dijkstra's algorithm or the Bellman-Ford algorithm. As with our unoptimized paths, we can combine the optimized paths to get a more optimal difference graph. From here, we can add our improved difference graph to our original graph to get an improved solution graph. But whether this improved solution graph is actually optimal depends on whether our improved difference graph is optimal. Unfortunately, just optimizing the individual paths as we've done isn't enough. We also need to optimize the pairs of vertices we select to be the beginning and end of each path. To see how this works, consider this table, which shows the length of the shortest path between each pair of odd vertices in our original graph. Assembling the optimal difference graph amounts to selecting edges from this table such that no two edges share a vertex and the total weight of edges selected is minimized. This is called a minimum weight perfect matching, though I didn't know that back in 2020. Once we have our matching, we can combine the corresponding paths to form our optimal difference graph. One approach to finding the minimum weight perfect matching is just to try every possible matching. This gives us our first complete algorithm for solving the run every road problem. First, calculate the shortest path between every pair of vertices. Then, for each possible matching of vertices of odd degree, combine the corresponding paths to form the difference graph, and check whether the result is better than any other difference graph found thus far. After considering every possible matching of odd vertices, add the optimal difference graph to the original graph to get the optimal solution graph. And finally, construct an Eulerian tour through the solution graph to find a route which optimally runs every road. Now, this algorithm does solve our problem, but we won't find it to be particularly useful. You see, the number of possible matchings is given by this expression here, where n is the number of vertices of odd degree in the graph. Just to give you an idea of how quickly this expression grows, by my count, Noe Valley has 76 intersections of odd degree. This gives us roughly 13 billion possible matchings. Clearly, we're going to have to find a better way. Fortunately, though we might not yet have a way of efficiently finding the optimal matching, finding a pretty good matching is something that isn't too hard for humans to do. This is especially true when the graph corresponds to an actual physical space, and the weights of the edges are the actual physical distances between locations. This is my original planning map from April 5th, 2020. You can see I've marked a matching of the odd vertices along with the corresponding paths. It's still hard to know at a glance whether this is optimal, but I think you'll agree that finding a matching like this is significantly easier to do by hand than planning out the entire route from scratch. One caveat about the map, it includes an optimization that we haven't discussed yet, and is also using a slightly different graph than the one presented earlier in the video. So if it seems that some of the markings are missing or are in the wrong place, that's why. Unfortunately, despite my best effort at the time, I wasn't able to find an efficient algorithm to determine the optimal matching. At one point, I even thought I had a proof that this problem was in the same category of difficulty as the traveling salesman problem. In any case, at some point, there's nothing left to do but put down your pencil and paper and lace up your running shoes. On May 9th, 2020, I stepped out my front door at 4:30 a.m. If not for COVID, that would have been the starting date and time of the Quicksilver 100K. It was a cool and foggy morning, perfect running weather. It took me almost 7 hours, but at the end of it, I had completed my Run Every Road challenge. The full course was almost exactly 50 kilometers. I climbed almost 2,000 vertical meters and burned 4,400 calories. To this day, it is one of the accomplishments of which I am most proud. And for a long time, I thought that was the end of the story. Until something happened that not only revolutionized my understanding of this problem, but is the whole reason I decided to make this video in the first place. It is June of 2023, and those early days of COVID seem like a lifetime ago. I've moved across the country, changed jobs, and I'm reading this book. Both the subject and cover art might be familiar to you. Yes, it's our old friend, the traveling salesman problem. In particular, I'm partway through chapter 6, which tells the story of how researchers back in the mid-60s used an approach called linear programming to find solutions to specific instances of the traveling salesman problem. One such example is this 48-city tour of the United States, which we saw earlier in the video. Now, linear programming is an enormous topic in its own right, so I'll avoid going into too much detail, but roughly speaking, it's used to solve optimization problems where the constraints of the problem and the value to be maximized are both formed by summing constant multiples of the inputs. The book suggests that at the time, there was some hope for using linear programming to find an efficient algorithm for the traveling salesman problem. The difficulties of the problem weren't as well understood back then, and they had some reason for optimism. One of those reasons was a discovery made by Jack Edmonds, who used linear programming to tackle a similar problem. The book describes his problem like this. A perfect matching in a graph is a set of edges that pair up the vertices. That is, each vertex is the end of exactly one edge in the perfect matching. If costs are assigned to the edges, then the problem is to find a perfect matching such that the total costs of the edges in the matching is as small as possible. And my jaw dropped. This was the missing piece of the Run Every Road problem. The book goes on to say that he, Edmonds, is able to directly apply LP duality to obtain a polynomial time algorithm to compute minimum cost perfect matchings. That is, our problem has an efficient solution. My first thought was, I have to make a video about this. I was so excited, I immediately downloaded Edmonds' original paper and started reading. And I quickly discovered why I had never heard of this algorithm in any of my undergraduate courses. It is a beast, especially for someone like me who isn't an expert in the theory of linear programming. There is a much simpler version of Edmonds' algorithm known as the Blossom algorithm, which solves the problem for unweighted graphs. But the solution for the full minimum weight perfect matching problem is highly non-trivial. I spent about a week studying this paper and others that have been published on the topic before and since, and I think I almost understand how it works. Sadly, I had to concede that the details of this algorithm might be beyond the scope of what I could cover in this video. Fortunately, I'm not only a computer scientist and math enthusiast, I'm also a software engineer. And one of the perks of being a software engineer is that you don't have to do all the heavy lifting yourself. And so I enlisted the help of the Google Maps Distance Matrix API and the NetworkX Python library, which includes an implementation of Edmonds' algorithm. One quick note, you may notice that the documentation here and Edmund's original paper both refer to finding a maximum weight matching rather than a minimum weight matching. There's a simple transformation that can be done to turn one into the other or vice versa, so the maximum weight implementation can still be used to solve our problem. Now, with these powerful tools at our disposal, we're almost ready to find the optimal solution to our problem. But first, we need to identify the vertices that will be involved in our matching. Here's our neighborhood graph from way back in chapter 1. Just like we've been doing all video, we'll color the vertices based on whether they have odd degree or even degree. Next, there's an optimization that can be used to reduce the number of odd vertices we need to consider. Since dead ends can only be run in one possible way, we don't actually need to include them in the graph. However, this only applies to true dead ends. Remember all those stairways we talked about back at the beginning of the video and how they might be used as shortcuts? Now is the time we have to worry about that. A road like Cesar Chavez east of Castro is a true dead end. Your only option is to run it from end to end and then go back the way you came. But 27th Street west of Douglas has a shortcut to Diamond Heights Boulevard via Sapphira Lane. It may be optimal to use the shortcut, or it may not be, but the algorithm may not even consider it if we drop that vertex, so it has to stay. On the other hand, if you've decided not to allow shortcuts in your run, then all dead ends are true dead ends, and you can safely remove all of them. Removing just the true dead ends from our graph gives us this. One side effect of this optimization is that now we have some vertices connected to only two edges. Since these are basically indistinguishable from a straight road with no intersections, we can remove those vertices and add an edge that directly connects the vertices on either side of them. All the remaining orange vertices are the ones that need to be included in our matching. If you count them, you'll find that these are the 76 intersections of odd degree I mentioned earlier. Now we're ready to use the distance matrix API to get the distance between each pair of odd vertices. Now I have to confess that Python is not my native language. My friends who are Python programmers tell me my Python is disgusting and looks like it was written by a C programmer, which, to be fair, is spot on. So we won't linger here long, but there are a couple things I wanted to mention. The first is that Google caps the size of the distance matrix we can request at 25 for both the width and height, and 100 for the total number of elements. That means we have to break our big distance matrix into sub-matrices and make a separate query for each one. If not for these restrictions, all of this could be replaced with just 3 lines of code. Second, I'm specifically asking Google for the walking directions between the vertices. This is so that we can take advantage of some of those shortcuts we were just looking at. If we wanted to disallow shortcuts, we would instead ask for the driving directions, which would keep us strictly on the roads. Next, we feed the distance information to Network X using this pleasingly concise code snippet. And the result is this, our minimum weight perfect matching. It looks like the algorithm did take advantage of quite a few shortcuts, including Sapphira Lane and the stairs at Cesar Chavez, 27th Street, Valley, and Duncan. In some cases, we'll have to add additional vertices to our graph to accommodate these shortcuts. Finding the corresponding shortest path for each of these pairs and combining them to form the difference graph gives us this. And adding the difference graph to our original graph gives us our solution graph. Now we just need to find an Eulerian tour through this graph. You'll recall that in order to do so, we need to break it into loops. Any loops will work, so we should try to take advantage of that fact by choosing routes that are simple and don't involve a lot of unnecessary meandering through the neighborhood. That is, as much as possible, we should try to run an entire road from end to end before turning onto a different street. For example, we might find this loop. Now, this loop might not seem particularly intuitive or easy to follow until we consider the locations of these vertices on the original map. Then we see that this circuit has us running all of Castro Street, followed by all of Noe and Sanchez Streets. Then we run Church Street with a quick detour down Comerford Street and back. And finally we run Chattanooga, Vicksburg, and Hill Streets in their entirety to finish off the loop. We can decompose the remainder of the solution graph into similar loops, such as this one around the perimeter, this one which picks up most of the east-west streets north of Clipper, this one which picks up most of the east-west streets south of Clipper, and this one which picks up the rest of the neighborhood. Combining all 5 loops and adding back in the dead ends we took out earlier gives us the full optimal route for running every single block of every single road in Noe Valley. Now, before I show you the grand finale, I just want to say a sincere thank you to everyone who watched all the way to the end of the video. I put so much work into it, it really means a lot to me. If you haven't already, I hope you would consider subscribing and perhaps taking a look at some of my other videos. I'm especially proud of my recent videos on primality testing and Project Euler problem number 60. And now, without further ado, may I present our solution.